Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to continue looking at the Central Limit Theorem. Central Limit Theorem. Now, let's start out with a summary of what we had learned. Remember, the Central Limit Theorem says we took all possible samples, so all possible samples of size n from, and here was the amazing part. The amazing part is this: from any distribution. From any distribution then the result is a normal distribution, with, and here are the key parts, with the mean of the sample means, that's what that's called, is equal to the mean of the population. Those are the same. Okay, so this is the mean of sample means. Mean of sample means. That was number one. Number two, what we found was that the variance of the sample means is equal to, is equal to the variance of the population divided by the n, the size of the samples. And then from 2 came number 3. If you take the square root of both sides, we said then that the standard deviation of the sample means is the standard deviation of the population divided by the square root of n. And we often call that the standard error. The standard error of the mean. Okay. Now, there's something interesting that happens that you may think, oh, those are just formulas, they're numbers, it doesn't really seem that important. However, what I'd like to do is I'd like to show you why this is so important. And so I'm going to add to my picture here. I want to add, not that, I want to add this. So what is that? That is a standard normal distribution. So it has a mean of 0. Let's go with the white, I guess. Has a mean of 0 and standard deviations of 1, 2, 3, minus 1, minus 2, and minus 3. Now, there's something that amazing happens that you wouldn't just see it numerically, or the numbers, the formulas may not make sense until you see it graphically, and then we're going to do an example. So, the next thing is consider, or let's just graph. You know what? Let's just do this. Graph the normal distribution I could have just written it this way. Anyway, the normal distribution n, it also has a mean of 0, and it has a standard deviation of 1, and n is equal to 4. So groups of size 4. So really, I should have written this as the normal distribution of 0, 1 divided by the square root of 4. That's what this formula says, right there. Well, how does that change everything? Okay, well, let's do this. Let's use the empirical rule. So, for example, if for the we'll do the normal distribution here. So for the n0, 1, if I asked you the probability that z is between -1 and 1, well, we could We know that from the empirical rule, that's 0.68. There we go. And we're done. If you use the tables, you get something it's like 0.6815 or something really close to that. Now, let's change it. Now, let's do this. I should have coincided my colors better, but this will work. Now, what about the normal? That's not very bright. What about the normal distribution that has a mean of 0, but the standard deviation now is 1 divided by the square root of 4? Well, the square root of 4 is 2, so let's think of it this way. Normal distribution, mean of 0, standard deviation of 1/2. Well, before we just rush into graphing that, think about what that means. If the standard deviation is now 1/2, then that means that there's 1 standard deviation from the mean at 1/2. 2 standard deviations, I'm going to come down, let's come down here. So this is 1/2. But now when I was at 1 on a normal distribution, now, oops, that was not 1/2. This is 1 standard deviation now. This is 2 standard deviations, and I'm already maxing out at 3 standard deviations when I was not even very far out on the normal distribution. And if I go the other direction, here's 1 standard deviation, 2 standard deviations, 3 standard deviations. And the reason we don't normally write beyond 3 is because the numbers are so close to 0. It's they're practically 0 for most arguments. Now, so I have this drawn in. Let me show you. Let me show you what this actually would look like. This graph, so this graph means now, it means you get that picture there. So now, if I want to find the probability where z is in the same range from -1 to 1, well, what do I get? Well, look at this. If I was looking at the yellow picture was everything between those dotted yellow lines. But now look at the new picture. The new picture is everything in here. Well, if you're 2 standard deviations out now, what does that mean? That's all of that. Look at how much more we're coloring than we did before. In other words, the empirical rule says that's 0.95. So what happens with the central limit theorem? It also indicates that as you start taking samples that get larger and larger, then the average of those samples tends to get closer and closer to the mean. So whereas it might have been rather easy to find someone that was 6'6", not a difficult probability, 2 standard deviations from the mean, now a person that was 6'6", to get a group of them, just a group of 4 of them, would be 4, it'd be all the way out here. It would be 4 standard deviations. In other words, your chances of that happening is about 0. So it's totally changed. It's reasonable to randomly select 1. It's essentially improbable, not impossible, but improbable to select 4 people, 4 men that have an average height of 6'6". So you're kind of going off the charts already, even with groups of size 4. Okay, now let's try a problem. So what do we want to do here? So let's actually let's use the table. There's one other thing I wanted to show you, and that is this. So, the last property 3, property 4 is this. Property 4 says that now that the z-score, you're not for just a single data value, but for a data, the mean of a sample is now it's x bar minus the mean. Those shouldn't seem different, but now the standard deviation has changed from the standard deviation of the population to the standard error of the mean, which is sigma divided by the square root of n. And then that is how you would then apply these same problems. And so I wanted to, let's try one. Let's try this. Let's go to another screen. I want to take my picture here with me because it's so nice. That's just a good picture. Actually, I don't even need it. You know what? We don't need that picture. Let's go here. I'm going to turn this one off. And let's do this. Here's my picture. Okay, I think we're set. So, okay, find. Okay, actually, I probably do need both pictures here. Find the probability of randomly selecting a single male 78 inches or more. 78 inches is the same as 6 feet 6, as 6 feet 6 inches or more. Okay, now this is a key here, is a single male. Well, what we would do is we'd find the z-score. So find a z-score for 78. We're using the same data. Oops, I should remind us that the mean is 70 and standard deviation is 4. Okay, so 78, so we're going to take 78, subtract 70, divide by 4. That's going to be 8 divided by 4. That's going to be 2, and we knew that. And let's just actually look it up in the tables themselves and see what they give us. And so if you look up in the table, a value of z is 2, then that gives you an area of 0.9772. Well, I need to bring up one more picture here, because what I just found now is this yellow, we'll call it this orange area. So the 78 would be right there. Okay, so I just found this little tiny orange bit out there, okay, from 2 standard deviations onward. So now look at this. Area is 0.972. Well, what is that? That's all this stuff over here to the left. But we don't want the left bit, we want the right bit. So we need to subtract that from 1. So our answer then becomes the probability, oops, let's go back to our original color. The probability of randomly selecting a male greater than 78 inches is equal to 1 minus 0.9772. That's going to equal 0.0228. Okay, so it's not only 2% of the males in America are 6 feet 6 or taller. So it's pretty difficult to do. About 2 out of 100. Now let's change the problem ever so slightly. Let's change it by yellow. Yellow would say the same thing, but now it's going to be a group. How about a group of 4 males? A group of 4 males. Okay, so randomly selecting 4 males. Well, I already have that drawn. It's this curve, this blue curve. But remember, so let's first calculate a group of 4 males. So z-score is going to equal z-score for 78. Oops, that's going to bother me. The z-score for 78 is equal to the 78 minus the 70 divided by, now remember, it's the standard error of the mean. Well, the standard error of the mean is the standard deviation for divided by the square root of the sample size, which in this case is also 4. So this gives me an 8 over 4 divided by the square root of 4. Well, that's 4 over 2. Well, that's 8 divided by 2. That's 4. Now, before I go on, for those of you, most of these you have to use a calculator. If you're using a calculator, you need to enter this in the following way. I would type it as 78 minus 70 divided by parentheses 4 divided by the square root of 4 parentheses. If you forget those bottom parentheses, then you can sometimes get some error. We don't want mistakes. So that's how I would put that into my calculator, and you should get 4 as well. Okay, now let's look at our picture. Our picture over here, so now we're talking 4 standard deviations. Well, that's 1, 2, 3, 4 standard deviations. On the blue curve, though, not the yellow curve. It's just this little blue line, that little sliver out there. So let's find the probability. Well, if you look on your table, the highest your table goes is to a z-value of 3.49. We're already at 4. That's a problem. So what do we do? Well, if it was a table and you only had access to a table, you would say the probability of a probability that x bar is greater than 78 is essentially 0. You could say that, essentially 0. Now, for those of you that just like a calculator, your calculator also can do this for you as well if you use your function normal. I'll show you how to do this. Normal, CDF, and then you're going to enter the left value. So the left value in our case is going to be 78. Our right value is going to be infinity, and infinity for your calculator is E99, comma, and then you're going to enter the mean, 70. And then the standard deviation. Well, the standard deviation is 4 divided by the square root of 4 parentheses. And let's actually get a decimal number for that. I'm going to take you over to my calculator, and I'll show you how to do this. This is for a TI-83 or a TI-84 calculator. So here we go. So I'm going to go to my graph and calc. Looks very calculatory. And let's clear this. So what I do is you have all these buttons, go to where it says distribution, D-I-S-T-R. So you're going to have to go second, and then the distribution button. And you're going to pick the second option, normal CDF. So choose that. And then it already tells you in the screen what to do. Lower bound. So our lower bound we said is 78, comma. And the comma, notice, is right above the 7, so comma. And then we have to get infinity. And the infinity in our calculator is the capital E and then a 99. That's scientific notation. So what you do is right above on the comma key, you see where it says EE? Well, and you're going to press EE and you're going to get E. So ready? You're going to go second comma, and there's the E, and then 99, comma, and then our mean is 70, and our standard deviation is 4 divided by the square root, and notice the square root is that yellow character up above this x squared. So you go second square root 4, and then I have to arrow out of that, and then a parenthesis, and I press enter. And there's my answer. I'm going to round it 3.17 E minus 5. 3.17 E minus 15. So this is equal to 3.17. And then it said on the calculator, it says e to the minus 5. Well, that means e to the 10 to the minus 5th power. In other words, what you do is you move the decimal 5 places to the left. So you're going to create 4 zeros. So it's going to be 0.1, 2, 3, 4 zeros, and then the 317. And that would be your actual numerical value. This is, notice this is tenths, hundredths, thousands, 10,000s, 300 thousandths. So 3 out of every 100,000 people would be your odds of that happening. Okay? And that's how you can use the calculator, and it shows you the difference between a single selection and then a selection that is represented by the average for a group. And welcome to the Central Limit Theorem. Hope that helps. Thanks for watching.